Thanks, Andreas. Thanks, Bob, for inviting me to come talk. So, my talk is on... Anyway, it has something to do with entanglement, classical structures, and entanglement classification. So, if you've seen a talk by Bob recently, or one by Ross recently, you've probably seen red and green dots. Which I'm going to give you a bit of an introduction to those, but in kind of a different way maybe than you've seen before. A different, equivalent way. So, what's that? Anyway, so, like, everybody that's done quantum information has done quantum circuits. So, you know, we draw the tensor product this way, and somewhat controversially, we draw composition this way. So the thing that everybody uses when they talk about circuits is controlled NOT gates. So these are pretty straightforward thing. You have a qubit here, comes in, decides if you want to do a NOT over here. And if you have these and a couple of other little gadgets, you get something that's sort of computationally universal. So one of the ways you can think about these dots is think about trying to sort of break down what this C-NOT gate is. So you kind of ask, what's going on when we make a C-NOT gate? And it's kind of like we have a control bit coming in, and we want it to come straight back out, but we also want it to do something else, so we make a copy of it. So this will be our sort of copy a bit operation. So one copy comes out, and then we want the other copy to come down and sort of decide whether to do a NOT or not. And what this is called to a computer scientist is just XOR. And thus sort of justifying why it's drawn that way. So, so you know, this thing's just an XOR, which I can draw sort of suggestively with kets. 0. Right? So now you think, okay, well I've got something that looks like this. It's a copy. It's sort of like a co-multiply. So it's a co-monoid. So you think, what would the unit for this be? Well, it's actually the thing that just sort of uniformly deletes anything you copy. So if you copy it, you want to uniformly delete both inputs. Which, in our cases, in a tensor world, uniformly delete means just carry both things to 1. And we have something that does that, namely bra plus. I mean, we have a couple of choices for that. So that does that. And this gives you a co-commutative co-monoid. And the other thing we have if this is painfully boring, you can let me know and I can speed things up. But is this guy, this XOR. And it's associative and commutative and all that kind of stuff. And we have a unit for it as well. Which, what's the thing that you can XOR with anything and get the thing back? Just ket 0. So this thing gives you a commutative monoid. So we have a commutative monoid, a co-commutative co-monoid. And since I've been drawing kets rather than bits, we're actually in something like Hilbert spaces. We have an involution which turns things upside down. So this, we actually have sort of a co-XOR. And this guy, we have a sort of a co-copy or a fuse. Which there's sort of an intuition to these, but really it's just the, if you're thinking about qubits, it's just the conjugate transpose of the matrices or whatever. So, if we take say, this pair of guys, and we stick them together, we get this thing called a special Dagger-Frobenius algebra. So what this does is, well, we have all the things: associativity, co-associativity, co-commutativity, all that kind of stuff. We additionally have this nice thing called the Frobenius law. And we have another thing called specialness. Which is just this sort of an isometry property. We're saying we haven't really done anything by doing something that's sort of our code thing, and then by co-multiplying and then multiplying. So this thing gives you a special Frobenius algebra, Dagger special Frobenius algebra. And so does this thing as well. They both give you kind of the same kind of thing, sort of two different rotations of it.
Can you explain the dual of the XOR again, please?
The dual of the XOR. Okay, so if you think about XOR just as this linear map, then the dual of the XOR is the conjugate transpose of that linear map. So it's sort of like you can think about this thing as actually copying the other bases. So that one sort of copies the zero bases. This dual of the XOR actually copies the plus minus bases. So is that? So
the linear algebra can join the matrix.
yeah.
What does it mean to legal?
Good question.
That is a good question. It's physically, well, on this level, this is sort of the gadget that uniquely identifies the eigenvectors of the Pauli Z matrix, and this is the gadget that sort of uniquely identifies the eigenvectors of the Pauli X
You
matrix.
should ask the engineer in the audience. They wrote a paper about that one. Fusion, your fusion paper, Bill and Brown.
Okay, so anyway, we have basically these algebraic things, these two Dagger Frobenius algebra, and they're special. So you get this this really nice theorem from them.
It wasn't me that asked the question.
What?
It wasn't
No.
me that asked the question.
They asked what this thing was. I said it's the fusion you use in your paper with Dan Brown to build clusters.
But it wasn't me that asked the question.
Huh? No?
Right. Anyway, what these things do is that you can take any sort of convoluted graph of multiplies, co-multiplies, units, co-units, like this. I'll try to have some discipline in how many legs I put on these to start with. Does that look like I've seen something? Yeah. Okay, and you count the inputs, and you count the outputs, and that's the uniquely distinguishing characteristic of a connected set, one of these. So you can always say that this equals some canonical way of drawing it. So maybe I'll put some extra inputs here. Two. So
You've got too many inputs now.
Yeah,
what's that?
You've got too many
you've got
inputs
4
now.
inputs on the right and 3 on the left.
Oh, yeah. So anyway, it doesn't change the number of inputs, but so basically this is the sort of so-called spider theorem, or kind of the unique factorization of multiplying, co-multiply, sort of proven in a lot of contexts and stuff. But we call it the spider theorem, and basically use it to justify the fact that anytime we have a connected graph with just one of these special Frobenius algebras in it, we just draw it as a big one that's got however many legs we want. So this property is satisfied for that one, and it's also satisfied for this one. And this this is essentially how you can sum up what a special Frobenius algebra is.
Just to, to avoid me getting utterly lost, I'm trying to do the linear algebra in my head.
Okay.
Am I right that the upside down version of exclusive OR, you send in a 1, for example, and that will become a superposition of 0, 1.
Right, exactly.
So that means that the right way up exclusive OR is actually a rather, the more is going on than meets the eye, because to preserve amplitude, you have to send in that superposition to get
Oh yeah, definitely.
1. If you send in something ordinary like 0, 1, the choice, or 1, 0, the choice, you'll get your 1. But sort of the strength of the universe, as it were, will have been deflated by a factor of root 2 or something. Right? You have to do the entire wavefront, the entire system.
Well, and sort of specifically when you put in the thing that's not copied by your op, you specifically get the Bell state. So that's partially the point of these as a method of talking about entanglement.
Okay. Well, even more worrying is, or maybe not worrying, it's desirable, but if you put in 2 different things instead of the same thing to your anti-copy, it just destroys the universe. It becomes 0.
Yeah. Okay, I'll get to these things. So these things are both special Frobenius algebras. Individually, they both have these properties, and they have this nice spider property, if you take it. But together, these two have a special relationship, which is basically, and to save you guys that have been sort of sprawling the linear algebra, or doing it in your heads, sort of write out explicitly what these things are for qubits. So we write these co-multiplies basically as copy operations. And of course, their multiplies are just the dagger of that. And these have the property that they correspond to these bases that are sort of maximally non-commuting. So if you have your z basis here, your x basis is sort of here. And these actually satisfy axioms to make them complementary classical structures. So in addition to this nice spider theorem, which you get from this, you get some other properties. Who can I use? I guess I can use this guy. So let's see. I'll go back to sort of the familiar variants. So if you do, oops. So if you copy, and then you do XOR, you might as well have just done XOR first and then copied the answer. Now the other thing, if you remember sort of the definition of these unit points, they're exactly the things that these other maps copy. So if you take the unit for copy, which remember this was raw plus, and you put it here, this thing actually gets copied. And sort of symmetrically like this. So this is actually enough to make the sort of diagonals. So if you take the dot comonoid with the plus monoid and you use them together, you get a bialgebra. And dually, if you sort of take the other diagonal, you get a bialgebra. So you get these properties and you get the sort of the dual of all these properties. So this complementary thing actually gives you a pretty rich algebraic structure and lets you do a lot of things sort of talking talking logically about entanglement. One more requirement that I make that works in this specific case, and it's actually sort of something we're hashing through to see where it works more generally, is that I want these things to have kind of a matched compact structure, which basically means we want these two things to be the same, which sort of justifies why we just write it as that. So, specifically, a result of the spider theorem is that we get sort of this idea. But we can also sort of mix them since we've given them the same structure. And this actually generates a compact closure on the objects we define these things over. In a sense, we're giving ourselves the ability to create traces and draw kind of arbitrary graphs of these things, and not just limiting ourselves to sort of strict directed acyclic things.
Just to clarify what the kind of grand theme of the thing is, what you're sort of claiming or having as a theme is that even though real controlled monoidal things are not made of these subcomponents, the subcomponents would be quantum illegal things.
Right.
Conceptually
Right. Yes, it's a sort of a conceptual framework of saying kind of when you do a C-naught gate, sort of conceptually, what do you have sitting inside of it? And often certain collections of these things can build real-life things, specifically real-life entangled states and real-life unitary transformations. And you can break them into more primitive things and sort of reason about what they're doing to each other.
Alright, but you have to then have a kind of meta rule that people who are innocently playing with the subcomponents that are in fact the legal objects of our world must never be allowed to accidentally put them together in a way that collectively is an illegal object of our world. Is that easy to do? Is it a simple syntax requirement?
It's this language is. Well, can we talk about this?
Yes, of course.
Okay, so this is sort of our core language, and this language makes sense in any dagger monoidal category. So if you're in a category that's got a tensor product and it's got a dagger, it's got an involution basically, then this makes sense. And these special Frobenius algebras, and they're all sort of well understood terms of props and all this other kind of stuff. So this is a pretty solid core language for reasoning algebraically. But what we want to do is really talk about entanglement. We want to talk about real quantum things. So as a conceptual framework, this is kind of a start. But we want to start talking more about sort of Hilbert space quantum mechanics and that sort of thing. So the thing we do is we start extending this language a bit. We talk about extensions. The first thing we want to do is, okay, so we have a deleting point. Well, that's already a basis vector, or it's already something like a basis vector in the category you've defined. But there might be lots of them. So we really want a set of points, and these are all the points that get copied by the other one. So we have a set of sort of index set, probably a finite set because we like to work in F-Hild because it's compact closed and all this sort of stuff, such that these things get copied. So these sort of give us these give us these classical points. So these pairs, monoids and comonoid things, are classical structures, or these special Frobenius things. These are their classical points. This sort of gives us a concept of a whole basis to reason about. And as per your comment before, you get things like, say, our 0th classical point. If we put it with our 1th classical point, we actually get a big ugly 0 that obliterates our whole graph. So there are sort of caveats for working with these things. Sort of a conceptual price you pay by putting them in language. So more than just classical points, these things, well, they give us classical maps. So if we have our copy like this and we feed it a classical point, if we fed it the deleting point, we actually get the identity. But if we feed it some other point, we actually get a map like this, which is actually, in the term of Hilbert spaces, it's going to be a permutation on the basis that this point is over. So for instance, if this point is the one that's copied by plus, then this gives us a sort of not permutation on the standard basis, all this kind of thing. And that's done some good work for us. We can actually define quite a few states. So, as I mentioned before, we can get a Bell state like this, sort of our compact closure. If we feed sort of the other classical point into this guy, which I'll write him as 1 for now, we actually get an EBR state, which does a similar job for you, but sort of can have some different concrete properties. And something that gives some kind of new intuition about what these things are is if you take this guy and you use that cup that I defined earlier, sort of this cup, to bend his leg over like that, you actually get a GHZ state. So in terms of three-partite entanglement, which is really what I'm going to talk about, and well, the meat of what I'm going to talk about, maybe I'll say some things about 4 and above. The GHZ state has a special role, and so does the W state. So that's this guy. And the reason these guys have a special role in three-partite entanglement has to do with slop. So I imagine anybody that's done entanglement theory has heard of lock, at least, which is local operation, classical communication. It's essentially, if you have some state like this, you can do kind of local unitaries on it to turn it into some other state, state prime. Then we say that these two things are equivalent under lock. So this does a lot of work for you in bipartite states. In fact, it sort of closes the book on bipartite states and says we have kind of this total order of lock classes kind of continuously growing from the least entangled, the separable states up to the lock class that the Bell state's in. When you go to three-partite, there's a big mess of them if you go to lock. So a number of years ago, Durr, Serac, Vidal, and some others, they did SLOC. So the S is for stochastic. So rather than just local operations with classical communication, you have stochastic local operations for classical communication. So before, where I said unitary local operations, now I just mean invertible local operations, which it seems like a small tweak. Well, it probably doesn't seem like a small tweak if you're a physicist, but it really collapses the three-partite case down to saying, well, up to SLOC, which is kind of like lock cares about how much entanglement you have. SLOC cares about if you have entanglement. Up to SLOC, you only have two genuine three-partite states. You have this state and you have this state. So, so basically, we want enough mechanism in our language to talk about this state. And a way we can do that is to get ourselves a little bit closer to Hilbert spaces in our graphical language. And the way we do that is to introduce phases. So this is something that's a little bit better than classical points. We actually introduce sort of arbitrary phases on our points. So in the case of qubits, this is actually just a local complex phase between our basis vectors. So this would sort of be defined as like this. And this gives us a whole lot. Actually, this gives us everything, because now, in addition to having classical maps, yeah, they're still here. We have phase maps, which are unitaries in kind of one local dimension. And these things commute with the dots of their same shape. So this commutes with dot, and the sort of the plus one commutes with plus. They're additive, and they do a lot of things. And we can actually get arbitrary unitaries just by composing these things in the right way. So this is just a Euler decomposition of a unitary. It's just these three sort of local phases. So this one's on sort of the canonical basis plus basis, computational basis, well, computation plus basis. So if we have 1 qubit unitaries, I've already showed you C naught because that's kind of where I brought this from. You can do everything. It's kind of computationally universal. So I've said now we can do everything. So at least we ought to be able to do a W state. And we need a couple of sort of identities on phases before we can do that. So how do we get our classical points back by saying the 0 phase and the pi phase are sort of, this is going to be plus, this is going to be ket minus. And we have identities on phases that I'll maybe just show you a couple that we have. So if you've got one of these sort of classical gates, these things commute past each other with a change of sign. And you have this supplementary condition, which is a sort of a cooked up thing, but it's getting more natural as we ponder it a little more. Where if you have this kind of situation, where you have an alpha and a beta sort of sitting between these two guys, that you actually get a disconnect, leaving a gamma behind, exactly when alpha plus beta equals gamma, and gamma is classical. So this is exactly enough to describe the behavioral characteristics of a W state. So the way we distinguish these slot classes of a GHZ state and a W state, one way we can do it is by plugging. So if we plug a 0 into a GHZ state, we get 0, 0 left over. So I'm saying if we project the first qubit to 0, we get 0, 0 left over. If we project the first qubit to 1, we get 1, 1 left over. So no matter what we do, we're going to separate the thing. I'm talking across, of course, the basis it's defined in. Now with the W state, that's not the case. Because if we plug a 1 in, we get something that separates. We get 0, 0. But if we plug a 0 in, we get an EBR state. So we get true entanglement. So for an input of 1, we get this thing. Let's see, an input of bra 1. For an input of bra 0, we get this thing. So this was our classical map. We've sort of taken it and we've bent one edge over and we've gotten an EBR state out of it. perhaps what I should have said was an input of 1, like that. I'm just saying sort of plugging into the first qubit, this kind of thing. So, operationally, we like to view GHZ states as something that always separates. W states as something that's kind of like a switch. It's almost like a transistor, like the input is kind of telling you whether to disconnect or not. So we can take all of these identities we've made and chunk them into a rewrite system. And we can do automated rewrites to show theorems and stuff. So, provided this comes back on screen, I can show you a bit of the progress we've made toward this. So, let's see. One of the first examples they show you in the circuit model of quantum mechanics is the way you do a qubit swap is like this. You do a controlled knot here. Oops. You do a controlled knot here. You do a controlled knot here. So, real simple example to sort of swap the qubits. Now, if you think about these copies, these copy things as green dots, this is where we go back to the red-green world if you've seen this stuff before. And you think about the pluses as red dots, then this is what it looks like. Good. See that? So this is kind of like having 3 C0 gates lined up in this alternating order like this. So to make this a little easier to see, go ahead. These are just boundaries, these little funny gray things. I'll lock them in place so that Graph's wonderful layout capabilities don't mess up what I'm trying to show. And we normalize with respect to these rules that I've shown you so far. And this is basically just the core rule set. This is the Frobenius plus bialgebra. So we apply the bialgebra, we do a spider, we do a spider, we do a hop flaw, spider, spider, and we've done a swap. So this shows that even with the core language, we've actually been able to do quite a bit. We can actually, we can roll back through this thing, and at any point in time, we can sort of select everything and kind of make a choice of what sorts of things you do. So you can go through this kind of interactively. In this case, it doesn't matter too much because we're working with a confluent subsystem. But in some cases, if this doesn't work as advertised, then I might have to do a little manual work. Okay, so this is actually what a W state looks like. And basically what we wanted from a W state is to symmetrically control whether we entangle things or not. And this does the job, and I'll show you how. So by plugging, we actually mean, let's put in a red vertex. So I put in a red 0. This is the same as sort of plugging ket 0 into our W state. And if we do a normalization here, we do a spider, we do this pi action that changes the sign, we do a group action, we do a spider, spider, hop flaw, and we actually get an EBR state, and a disconnected thing, which a green phase like this is actually just a non-zero scalar, so we throw it out because we're working up to a normalization factor. So, if we roll back through this guy to here, and instead we put in pi, and we normalize, do a spider, make that 0, spider, go. And this is that supplementary angle thing. We get this, and we actually get 0, 0, the disconnected pair. So this is showing how putting this supplementary angle property into it has actually created the emergent property of the W state. So how much time do I have left?
Here's the show.
You're the sheriff?
Minutes, I think.
to have 25 minutes.
25 minutes? Okay.
No, no, no.
No, I've got a bit more to say. Though you guys might be going to the pub sooner than you expected. Any objections to? Anyway, so basically, we've done a lot to put these phase angles in. Like I said, we've got something that's computationally universal, which sounds great. We can make any unitary we want. We have ancillars. We can actually make any linear we want. But we're in Hilbert spaces. And part of the goal of this program was to say, well, Hilbert spaces are kind of hard. Maybe we should work with something that's a little easier than Hilbert spaces. So, so we'd like to do some things that are a little less heavy duty than having phase angles. I've shown you this emergent property of W states. Well, we can say this is a property that's emergent from putting in certain lower level rules. Or we can take this thing as our primitive. So our intuition kind of is that if this thing, which is basically our GHZ state, sort of has a status that allows it to be a primitive, then it's not a huge leap to say that W states, which all usually draw as triangles, shouldn't be a primitive. So the idea here is that these things are powerful tools with respect to rewriting because they have a lot of good properties. Well, they have one really good property, which is if you do this, you get something that's connected. If you do this, you get something that separates. So this is something you can use as a tool to talk about higher level entanglement. So if you think about any sort of in-partite system, entangled system, the first qubit is sort of like your control. You can view this as your control of two different kinds of entanglement. So this program put forward by Lamada and some other people is actually to inductively classify entanglement. So the idea is that lock is good enough for 2, slock is good enough for 3, but when it gets to 4, you have this problem in that you get finitely many slot classes for 3, but it's a degrees of freedom issue that you get infinitely many slot classes for 4, and that's because if you have something that acts as a control bit, if you have a 4 qubit thing. Something acts as a control bit here to make one of 2 3 qubit things. Well, you've got all kinds of sort of slot freedom in here, but these can have kind of a local slot difference in them. So the idea is to identify classes where we can sort of slock this thing into something where we can slock these into things we recognize. So right now this program is going in the way of sort of building states to witness entanglement classes like this. So one example of such an entanglement class, we might say that if W is like a controlled EBR state, sort of a control between EPR and separate. Maybe we want something that's kind of like, in a 4-partite situation, a control between sort of separate and GHZ. Well, you looked puzzled by this last statement. Maybe just, so the idea is we want one bit coming in that's going to decide what we get out is a 3-partite GHZ state or a totally separated state. And if we take W as our primitive, it's really easy to figure out how to do this. And that's sort of it. If we have a W like this, and we have one of these classical structures here, sort of a GHZ thing here, we make this our control bit, then if we plug this in, we'll get a pi, and this thing will be a GHZ state. If we plug this in, then we actually get something that separates here. And then this gets copied via our copy law. And we get something that separates. So this is sort of the program for moving forward and describing these higher entanglement classes sort of inductively. It's pretty fresh, sort of kind of lots of different ways we could go. But that's the general idea. So in the future, we sort of want to crystallize this and think about what parts of the language we want to make primitive, what parts of the language are like really critical to what we're doing, that sort of thing. Also, I want to say this was joint work with Ross, Bob, also Lucas Dixon to make the tool. Thanks.
Yeah, sure.
Now we've got.
Other questions?
Well, I can't help thinking that more or less exactly 20 years ago in some other part of this building I saw Yves Lafont drawing diagrams like this. Now I'm not suggesting to you that it's not original because your diagrams, there is difference here, but I wonder whether some dialogue with the linealogic people, I mean the French linealogic people might produce some interesting results, particularly Yves.
Yeah.
The linear logician among us may have something to say about this.
In combination with Simon Perdue, we have been talking with Yves Lafont and also Ian Mackey also worked on combinators. But it's quite a different kind of system because they're very sequential in the way that they rewrite, whereas this is not. It has kind of a different flavor.
So I'm not saying it's the same thing.
But yeah, a lot of these things seem to be sort of related and interconnected.
At the level of the compact closure, like which is without the dots but just with the line, then this is very close to proof nets, just the ordinary proof nets. Like the one from that community who's now moving in this direction is Paul-André Méliès, who's starting to use this for variance algebras now to sort of enrich the whole linealogic proof net thing. I guess John Bias is even now moving in the computer science direction of this sort of things too.
What's in the future for all this stuff then?
What's in the future for all this stuff? Well, right now a lot of the ways you can classify entanglement, they're very concerned about being exhaustive and saying like, when we're in this many qubits, this is how we can classify everything. We want to put everything in these sort of disjoint superclasses. Whereas I think what's a more interesting question is what algebraically you can do. So these things like W actually forms a really interesting algebraic structure. A couple of different ones depending on what kind of categories you look at it in. So you want to see algebraic properties that are sort of independent of this sort of idea of we want to cover all of Hill. And I think that might sort of illuminate how to design different kinds of protocols.
Can you see in this picture that, I mean, the difference between W and GHZ, in that GHZ kind of maximally violates the principle of local realism in that Merman type way. And whereas W doesn't necessarily do that, well certainly in his examples it doesn't do that. Can you see the difference between the two states from this picture in that respect?
I'm not sure exactly. Like this difference is sort of it's reflective of the fact that with the GHZ state, the entanglement is all contributed to something that's sort of shared among all the parties. They sort of have all subscribed to this one tripartite entanglement, whereas the W is kind of sort of equally shared EBR state. I mean, that's how it was originally defined, was equally shared EBR states. So I think it sort of illuminates that more pragmatic point of view. I'm not sure if that's really getting it.
I can actually say something more. Spectrums and bilateral time, we did some work looking at the GHZ state in this sense, and it turns out you need be more explicit about additional structure. For example, this phase structure, as Alex was thinking about, which is something which follows from the abstract structure, that you get a group structure there. If you take Z4 as your phase structure, then you get your violation of local realism. If on the other hand, this happens to be Z2 times Z2, then you actually get Rob-Speckens hidden variable toy theory, which is one of these epistemic theories Terry was talking about, which doesn't violate local realism. So it does give you a handle to analyze the situation. So,
Interesting.
So when you say if you take some choice, what do you do?
so when you take, there happen to be models, there happen to be two models, existing models, which is Rob-Speckens' toy theory, and which is stabilized quantum theory, each having respectively Z4 or Z2 times Z2 as these phase groups. And it seems that that's enough to either do the Mermin argument or not. It's really, you just derive from the group structure. But this is something you can do within this formalism, but it's not directly related to GHZ versus W. It's really about GHZ plus additional phase group structure either violates local realism or not.
So you mean you can use this whole apparatus to
Yeah.
analyze
Yeah, you
toy
can.
models as well as...
Yes.
That's sort of the thing that's nice about these is they make sense in a lot of different kinds of categories, like especially EFRA, which sort of permits a lot of these different kinds of models and that sort of thing.
Yes, so for example, the toy theory of Rob-Speckens is a subcategory of and then all the machinery of what is a base, you're not working in vector space, so you ask yourself what is a basis. These dot things, they actually tell you what is a basis there. That's what comes out.
Any further?
Could I sort of ask a rather vague, what are the rules of this game question?
Okay.
Right, because, you know, you've got this sort of quantum mechanics that you want to model. And then you've got these sort of, you know, algebraic primitives. And as you go up, you know, more and more dimensions, you introduce more primitives, which presumably have,
Right.
the sort of relations between that and the previous stuff. You know, you have equations and so on. As far as you can tell, does it sort of keep going on and on like that with more and more primitives as you increase the number of dimensions? And, you know, how complex does the whole thing get? I mean, do you find yourself with more and more relations or relations between
I see. I would say well, right now I'm sort of working under the rule that kind of the magic number is 3, because well these are the well understood structures, because you have basically one input, 2 outputs, or vice versa. So you have monoidal, comonoidal structures, which is sort of your meat and potatoes combination type stuff. And the way Lamada and some people have gone about sort of building these things up, they make the thesis that if you know kind of your n-1 guys, you can get your n guys. And this even starts at 3, where you say your W is kind of a choice between two of your two-dimensional things. So I'm hoping because the W state has this unique sort of switch flipping ability, that's actually enough to be able to describe it.